Hello, everyone, and welcome to another Flan Talk. And today we have Michael Rizvi with us. He is a PhD student at the University of Montreal and Mila. And his research focus is to better understand the intersection between learning and reasoning tasks. But he's also interested in theory of self-supervised learning and representational learning. And today we have him here to talk to us about his new paper, Simulating Weighted Automata with Transformers. Thank you for being here, Michael. You can take it from here.
Thank you. Thank you for having me. As stated, I will be presenting how we can simulate automata with transformers. And this was joint work done with Maud, Clara, and Guillaume, which was recently presented and accepted at AI Stats. So I'm happy to share this with you guys. So to start, a quick presentation overview. Basically, I'm going to start by giving like an introduction and a motivating sort of speech as to why we care about this, what this is about, and where this kind of idea comes from. Then I'm going to quickly go over the transformer architecture, sort of to set the stage and basically clear out any ambiguities about how we're conceiving the transformer model for this analysis. And the rest of the talk is going to be divided into two parts. So I'll start by talking about weighted finite automata and give the results for that. Then I'll talk about the weighted tree automata, and finally I'll wrap up. So let's start. So yeah, the objective generally of this line of work is to show like sequential reasoning capacities of transformers. And by this, what we mean is really about the expressivity of the architecture. So we're interested in seeing what kind of like complicated constructions or interesting algorithms we could encode within the parameters of the transformer. And we're not interested really in whether or not gradient-based learning or any other form of like learning rule would actually get there. It's more so a result just to understand like the parameters and the way that this model is sort of manipulating inputs, what kind of stuff we can do with it. And for this talk, we take the lens of simulation. And by simulation, what I mean is we're not only interested in seeing whether or not we can encode the algorithm that does the thing inside the transformer, we want to encode an algorithm that can sort of show intermediate reasoning. So what do I mean exactly by simulation? Like I said, it's sort of like really showing steps. And this is an idea that, at least in this context, was previously presented by Liu et al., who was, I think, also on this seminar at some point. And they introduced this idea for DFAs. So basically, this whole idea is simulating for a DFA means that if you give me some word on some alphabet from sigma star, what I can do is I can output not only like accept or reject, but I could actually output the sequence of visited states. So here I have an example of like some DFA that counts multiples of 3 in binary. So if we take some simple word like 1, 1, we'd start here, I don't know, we'd go, and then we'd come back, and we'd have S0. So instead of just outputting accept or reject, we could sort of have the sequence S0, S1, S0, for example, as a given output. And so Liu et al. Showed this not only in terms of that we can simulate, but also in terms of shortcuts. So they showed that for a sequence of length t, because transformers sort of have a fixed context window, there aren't recurrent models. So if you fix some maximal sequence length t, we can simulate any DFA with a logarithmic amount of layers in the length of the sequence, and even O of 1, so constant number of layers in some cases. And so this is like this whole idea of shortcuts that they present, which is that the transformer that can do the simulation is shallow with respect to the maximal sequence length. And I'll go more in depth about these ideas after in terms of how they relate to our work. But for right now, the general idea of these kinds of theorems, that's also the kind of stuff we do, is it's sort of like you give me a DFA, you give me some like maximum sequence length, and I can guarantee you sort of as output of my proof, a transformer model that has like parameters which can simulate the inner workings on any word of length up to t, basically. And by simulate, obviously, I mean sort of this simple working definition I gave in the last slide. And so the question we asked about this is, can we do this for more complex models? And so it turns out, yes, in the definite and sort of the direction in which we extend this is towards the weighted side of automata and also towards trees. So I'll start by giving a quick recap of the transformer architecture, and then we can dive right into WFAs and all that fun stuff. So the transformer architecture that we use is quite similar to the encoder in the original transformer architecture. So what this means is we're sort of only looking at this part here on the left, and we're not considering the part on the right. So basically, the two main constituents of a transformer encoder is multi-head attention and MLPs. And the reason why I think it's interesting to consider only the encoder is that we're interested in the representation that's going to be maybe then used to generate text. We're not necessarily interested in the other part. And also from a more mathematical standpoint, the output can be autoregressive. So it's kind of a different type of result. So I guess this is like a simple overview, but mathematically speaking, the way we consider this is we have some input matrix that has like rows corresponding to like each part of the sequence. So the rows are going to be like each embedded token, for example. And then what we do to this is we apply this data-dependent transformation, which is called the self-attention block. So without going into like the math too deeply, what this does is it basically calculates some kind of correlation matrix between tokens that sort of weighs the importance of how important is each word or each symbol to each other symbol. And the self-attention block, a whole layer, and F attention, is taking H copies, where H is the number of heads, and concatenating the outputs together. And that sort of is what we consider as an attention layer. And a feed-forward layer is basically a simple MLP. And basically by chaining together attention layers and MLP a bunch of times, we get the full model. So one layer, as we consider it sort of as this in this previous slide, is one multi-head attention and one MLP. And I'm actually going to maybe say this again later, but I'll say this right now as well. We also consider something called hard attention, which is when instead of having a softmax, we basically take the output of the softmax and define a thresholding function. So say anything that's over 1/2 is going to be set to 1 and everything under is set to 0. All right. So next, I'm going to give a quick overview of weighted finite automata, or WFA. So basically, weighted finite automata generalize DFAs in the sense that they compute a function over a word instead of simply accepting or rejecting it. So that's sort of, I guess, the biggest takeaway from WFAs. And mathematically speaking, there's sort of three main ingredients, if you will, that make up this kind of model. The first is the initial and final weights, which in some sense correspond to the sort of initial and final state of a DFA. And then we have the transition matrices, which also there's an analogy with the DFAs in the sense that DFAs do this with Boolean matrices. But now here it's sort of like we're generalizing this to the transition matrix can be just any real matrix. And in the same way as for DFAs, we have one matrix per symbol in our alphabet, basically. And the way that we compute this function is the following. So we're going to take this sort of a linear, this combination of matrices. So what we want as input is any word from sigma star, and what we have as output is some real number. And you could do this over any other sort of like a semi-ring, but for the purpose of this work, we're just really considering the reals. So yeah, basically the way this computation goes is if I have some input x, which I split up into x1 up to xt, I can basically define it as being, I start with my initial weight vector, then I multiply the weight matrices corresponding to each of my symbols, and then I finish by dotting this with my final weight vector. So here I give a little example about how we could do this with like some simple automata. And basically here we're interested on evaluating this function on the word AB. And what we're doing is quite simple. And we basically just start in the state and we take the two possible paths and we sum them together. And each path is basically, we multiply together the transition of each weight. So if we look at just the first one, we have A, so 0.4, then B, 0.3, and then the exit, which is 0.6. And so by organizing this compactly with the matrices and vectors, we can write this same operand as basically just a matrix vector multiplication. Right, so now that we have some working definition of WFAs, hopefully that's clear enough, we can now attempt to explore the theoretical results we have concerning this. So we define sort of two notions of simulation. So I'll start with the first, which is what we call exact simulation. So exact simulation is basically almost the direct analogy to this simulation task of the DFAs. The big difference here being that what we mean when we say show steps. So essentially, given, I have this little example here, given some word as input, what we want as output is basically the intermediary states. So before we apply the final weight vector beta, what we want is to show the vector corresponding to the multiplication with the initial weight vector and each corresponding character. So first, for example, we have the word ABBA. So we're going to parse this by having the product between alpha and just the transition matrix of A, then with both AB, ABBB, and ABBA. So basically, this is sort of like what we mean when we're saying intermediary steps, given that we're summing over like all possible paths and that this is more complicated than just a sequence of visited states. The way we're considering this is really each step is like an intermediary step in the matrix computation that we're interested in. And so we also define a new notion of simulation, which is approximate simulation. So the only big difference between this and the previous notion of simulation that we define is this concept of like finite precision. So basically, the only difference is that now not only do I have to have some WFA, you also have to give me some epsilon. And so hopefully, if you give me a WFA and some epsilon, arbitrary epsilon, I can guarantee you potentially some construction, or I can guarantee you some function f, which can simulate a of x, which is sort of like the simulation of a being the WFA, sorry. So yeah, basically the objective is now I'm also playing with this epsilon. So we're simulating some automata up to some precision, and hopefully we'll see in the theorems how as we can make epsilon smaller and smaller, we can maybe still recover construction. All right, so hopefully that was sufficiently clear. So I'm going to try and go through the first theorem. So the big takeaway of the first theorem is that here we're making a couple assumptions. So before going into what the theorem says exactly, the first thing is here, note we're talking about bilinear layers. Bilinear layers are basically a type of like a MLP layer where instead of having one input, we have two, and the computation we do over these two inputs is simply like a bilinear transformation. So you could see it as a like basically contracting two sides of a tensor with this input. So it's a bilinear function. And to give some intuition as to why we might need this, if we go back here, we are trying to compose together matrices, which is a bilinear operation. So this is the reason why this might be interesting to us. So instead of having an MLP block after our attention block, here we're considering we have access to this funky bilinear layer. And the second thing that we're assuming here in this theorem is hard attention. So I mentioned this previously, but I'll try to go through this again. Essentially what this means is we have some thresholding function after the softmax, which is either going to put values over 1/2 to 1 and values under to 0. And so making both these assumptions, what we can say about simulation is that we can simulate any WFA with n states and with a maximum sequence length t in a log of t, and with the embedding dimension, attention width, and MLP width being a quadratic in n, and with a constant number of attention heads. So I guess this is the main theorem. And I find this to be quite interesting. We can't really recover this O of 1 here because of this notion of solvability that they use in the main DFA paper is not really defined to us. But what we can do here is at least get like a log t for any t. So as I said before, this is sort of like you give me a WFA with some number of states, you give me some maximum context length, and I can guarantee you a construction that's going to simulate perfectly with log t and quadratic everything else sort of. And to give an idea or sort of an intuition as to how we do this, the main idea is quite similar to the one of Liu et al. For this, which is to compute some version of the prefix sum algorithm. And the way we do this is essentially, after computing some embedding, the embedding here is going to be taking each character to its corresponding transition matrix. And then what we do is we compose them together in order to sort of in parallel compute each sort of prefix. And we do this over and over again, which can lead us to our output. And this readout is basically what's going to be then taking these and multiplying together or dotting them together with the initial weight vector, sorry. And so the second theorem is quite similar in terms of statement. The big difference is that we're basically removing both assumptions that we made. So previously, we assumed, oh, sorry, my Siri backed it up. So yeah, previous theorem, we assumed bilinear layers and we assumed hard attention. Here, we're removing this. We're using a regular feed-forward MLP and we're using regular soft attention. And the result that we have is that we can approximately simulate any WFA with n states at some maximum length t up to some arbitrary precision with a logarithmic number of layers, quadratic embedding dimension in the number of states, quadratic attention width in the number of states, n to the 4 for the MLP width, and O1 for the attention head. So basically what this means is you give me some WFA, you give me some maximum sequence length t, and you give me some epsilon, and I can guarantee you this construction with these number of parameters. What's interesting to remark here is that none of these parameters actually depend on epsilon. So I can always go get a better epsilon, and this doesn't really cost me anything more in terms of the size of my model, which is pretty cool. And so this has to do with the type of MLP construction that we used. All right. So that wraps up the WFA part of this talk. And so hopefully, yeah, we still have some time. Next, I'm going to talk about weighted tree automata. So I'll start by giving a quick refresher, sort of explaining what this is, how it works, and then we can dive into the results, sort of in the same sort of fashion as I did for WFAs. So yeah, the first big intuition for weighted tree automata is that they're the same thing as WFAs, but for tree structured inputs. So what this means is basically, what we're looking for at first is binary trees. And note that this is an example of a derivation tree. It's not a binary tree. And so by binary trees, what we mean is sort of any tree that has either no children or 2 children. And we're going to be assigning usually weights or values to the leaves of this tree, which is sort of why I chose a derivation tree as an example to put here, because there's an analogy or some analogy to make here. So what we want, basically, I'll show on this slide, is some little tree like this one here, where we have leaf nodes corresponding to letters from some alphabet. And aside from that, the tree has a construction which is binary, so either none or 2 children. We could actually extend this to arbitrary trees, but it's like it wouldn't be too difficult, but for the sake of this work, for the simplicity of the proof, we chose to focus on just binary trees. So what do tree automata do exactly? Well, as I said, what they do is really they take a tree as input and they compute a function on it, producing some output. So what they essentially, here's a little computation diagram of this. So if I have some tree, what I'm doing is essentially a recursive computation. So I start at the leaves, and in this case, what I'm going to do is take both leaves and compute some operation. Here, this is a bilinear operation, and big T is a tensor. So what we're doing is we're computing some bilinear operation with T to generate this intermediary state. And so we do the same thing with C and D, for example. And then we do this recursively again with these 2 new values we computed. We throw them through this tensor again. And we finish by basically dotting this together with a alpha, which is sort of like the equivalent of the weight vector that we had in the tree, sorry, in the regular automata case. So I think the general intuition is basically this, is we always start from the bottom when we go up and we compute each subtree recursively. And so this brings us to the definition of a simulation. So basically what we mean by simulation here, I guess in a analogous fashion to what we have for WFA, is that we can show the computation of each subtree with our transformer. So here, like I mentioned previously, if we have some simple tree here, what we're doing is we're going to compute each subtree recursively and sort of add this together. And what we want as output, for example, is V here being the embedding corresponding to like a specific symbol. What we want is to produce in some order the sequence of symbols and intermediary computations or subtrees, which are represented by these mu's here. So this is sort of like the main thing that we want. And one way that we try to achieve this, or the main idea for doing this, is how we can encode as a sequence. And the way that we do this is using parentheses. So as you can see here in this example with the transformer simulation, each opening parentheses corresponds basically to a node in the tree. And so this sort of lets us encode the whole tree as a sequence. And this lets us like treat this tree as a sequence and do computation with the transformer. So next are the theoretical results for this this weighted tree automata. What we have is basically we only have an approximate simulation result, and this approximate simulation result is as follows. So we can approximately simulate any weighted tree automata that has n states in length t up to some arbitrary precision, once again, some like given epsilon, with O of n embedding dimension, O of n attention width, and MLP width n cubed. And once again, here we have constant attention heads. And so what's interesting is over balanced trees, we can actually achieve a depth of log t, but over arbitrary trees, we can't do better than depth O of t. An interesting remark, though, is that in the worst case, the tree is completely imbalanced. So we have something like a comb, and this comb type tree is actually quite similar to what we would recover in the sequential WFA case. So basically, yeah. I guess the big scope of this work is we define the notion of simulation for weighted automata for both sequences and trees. So this is, I guess, the main contribution we have is that not only do we prove these theorems, but we also adapt this definition of simulation to two new contexts, which is a real weighted automata which compute functions, and also to automata that compute functions over trees. So yeah, we derive, as I said, the notion of approximate simulation and how we can apply it. And we show our pretty interesting results, which are that for both WFAs and WTAs, we can generally simulate in log of t. So WFAs, this is always the case, but WTAs, we have a log t for basically balanced trees. So that's about it. Thank you.